Welcome to the video on time changes and Levys characterization of Brownian motion. So we want to derive in this video two different representation of local or martingales in general. And the first one is time change characterization, which is in the lecture notes, theorem 6.4. Changes presentation. So roughly speaking, what it says, if I have a martingale, I can time change it in a way, so I can like modify the time scale in a way that it becomes Brownian motion. And here we want to, this theorem is in a slightly simpler setting, and we want to assume that we have an Ito process, which is an Ito martingale. So we have a function phi in our log, and this should be in a log for all t, right? So this is this space h2 log depends on the time horizon, and what we say is, okay, we can of course make t bigger and bigger, and then we want that this phi is in h2 log for all t. And now we want to consider a local martingale x, which is given as an Ito integral of phi with respect to a Brownian motion. Yeah. And now we have another assumption. We want to assume, in order to be able to time change this x into a martingale, we need to ensure that phi is somehow not non-zero, right? Because, well, would your phi just be constantly equal to 0? There's no chance that we can somehow time change here this process and turn it into a Brownian motion. So we assume that the mapping T mapping to the quadratic variation of this martingale. So this is here for this Ito process, we know what it is. So this is the integral of phi to the power 2 ts ds, is strictly increasing. And it goes to infinity, in the sense that if I integrate now, so taking the limit of t to infinity, this goes to infinity as well. Okay. So this is our assumption. This basically says I want that my phi is always non-negative, so that the quadratic variation of this process x increases all the time. Now I can define a time change process. So right here, I replace the t with a tau t, which I have to define in a minute. And then I claim that this is a Brownian motion where our time change is just given by the infimum of all u in our interval 0 to infinity of the first time that the quadratic variation gets bigger or equal the level t, right? So this is a stopping time. This depends on t for all t. And what I do with introducing this sequence of actually stopping times is I normalize the quadratic variation of this martingale x, or local martingale only, this local martingale x, to be exactly t. And this is, what we know for Brownian motion. If the Brownian motion is a martingale which has the quadratic variation equal to time t. Okay. And now I basically say, okay, if I take such a local martingale of this form, I can always time change it to be a Brownian motion in the way that I just need to normalize the quadratic variation. Proof. Okay, we want to show that this is a Brownian motion. We do it again in 2 steps. The first step is we want to prove that if I look at the characteristic function of the increment of x tau t, and then integrate to x tau s, and I condition everything on the filtration at time f tau s. This is nothing else than the exponential function of u square t minus s du, right? Because if I know this, well, this is pretty clear that this time change x is process x is normally distributed, and from this also follows rather simply in step 2 that this is an independent. I mean, the process has independent increments. This is all what we need to show because, well, this process, if it's at t equal to 0, I mean, this time change process starts from 0, 0, and it's a continuous process because x is a continuous process. So we only need to check that we have independent and normally distributed increments. And this is what we are going to do here. So how do we see this? So we make a like bit simpler. So let us introduce 2 auxiliary processes. The first one is z, which is just the exponential function of a process y. And y is defined as, again, okay, we work with complex valued processes, which is rather helpful, as we have seen already in the last video. And this is our process, right? So thinking of the martingale representation theorem, you might realize that we have considered such similar processes. Okay. So this means y is C valued E2 process. And this means we can apply E2's formula. If we do so, what is it doing? We want to apply E2's formula to Z, so the exponential of the E2 process Y. So what do we get here? So this is Z. So now, okay, if we at time 0, this is 0. So we have here 1, and then we have Z, right? This is an exponential function. So the derivative is again the exponential function integrated with respect to Y plus 1/2 to Z, right? The second derivative of the exponential function is still the exponential function, and then integrate with respect to the quadratic variation of S. Okay. Okay, let's plug in the definition of here. Let's plug in the definition of y. So what do we get? So you get 1 I times u of the integral from 0 to t of z phi s. All right, this is what's coming here, and then we have an integral with respect to the Brownian motion. Okay, and then we have this term here. Right, so we have u squared to divide by 2, and then integral missing t z y squared ts. And now we need to calculate the quadratic variation as well. So what we get 1/2, right? This is here, integral from 0 to t of z. And then what's the quadratic variation? Okay, the boundary variation term disappears. So we have here iu squared, and then we have phi squared ds, because the quadratic variation of the Brownian motion is just s. So this is nothing else than minus 1, right? I power 2 is minus 1 square, so these two terms here cancel. Cool. What is we have here? So this is nothing else than, just to write it once again, u t ds ds db. Okay. Okay, that's good. Well, so what do we know from here? Well, so that is C valued continuous local martingale, right? Because it's a stochastic integral. And we know that stochastic integrals are continuous local martingales. And okay, it's C valued because, well, it's C valued. This means that also the time change process here is continuous local martingale, just with respect to the time change filtration. Local martingale. This is what you can check on the problem sheets. Right? And we know that, well, by definition, if you take the absolute value of this time change local martingale, right, if you look at here the definition, this is complex valued, so we can bound it by the exponential of u squared 2 divided by t. Okay, so we have a bound, which means this is not only a local martingale, it's actually a proper martingale. So this is a martingale, t martingale, right? Because we can just apply dominated convergence to ensure, I mean, to get rid of the localizing sequence, because we have this upper bound here. Okay. But now if you think what the time change local martingale is, well, that time change with respect to tau t is exactly xt, x tau t, right? So this means we can apply now the martingale property to z to obtain that the exponential of p tau t, right? This is nothing else than z tau. By definition, how we define z, minus tau s plus ut square. No, sorry, it's not correct. I mean, this, here we go, plus this. Minus this, so this and this, I mean, this and this gives you tau z t. Sorry. Right, so we apply the martingale property okay, if I just point, I mean, okay, sorry, if I just point, right, I want to apply the martingale property of that tau t to this object, and okay, z is then the exponential of this object, right? So you can check the definition that this is nothing else. So yeah, okay, so I confused you. So okay, let me make this way. So here we use the definition of the tau and that tau s is martingale. This gives you the identity as we claimed. All right, so this is the first step. And now the second step is actually not super hard. So what we want to conclude that this time change process is indeed a martingale. So first, my step one, we note that if I take just the expectation of both sides, so what do you have? We know that characteristic function of tau t s here. Oh, sorry, here of course is one to show it as a martingale, so this has to be 1, right? This is a martingale, so it should be 1. So I take the expected value of both sides and I put this now on the other side, as I did unfortunately too early. So what do we get here? Exponential of u times s dt ds ds. Right. So and this means this is a characteristic function of a normal distribution. So I know that the difference here of x tau t and minus x tau s is normally distributed with mean 0 and variance t minus s. Okay, so now we just need to check that we have also independent increments. So what we know is here, okay, let's take an event A in the filtration f tau s, and we can again apply step 1, which tells us, okay, if I look at the expected value of IU and then the increment here, and then I condition it on the event A, well, this is nothing else than u times s dt sd ba, right? Right, because we have, well, this is on the other side, so we have then just indicator function multiplied with the constant. So this is the constant, and this is the expected value of the indicator function a, which is just the probability of a. Okay, and this is actually it, right? This tells us that the increment of x tau t in f is independent of the past, is independent of tau, of the time change filtration. Okay, cool. And now we can use this time change characterization of martingale, right? That every local martingale with respect to the Brownian filtration is time change Brownian motion. We can characterize, use this to characterize the Brownian motion as a special local martingale. And this is the contents of theorem 6.2, which is Levys characterization of Brownian motion. Okay. So what is Levys characterization? It tells us, so I have two properties which are equivalent. The first one is B is a Brownian motion. And the second one, and they are equivalent, is that BT is a continuous local martingale, and with respect to some Brownian filtration, right? There has to be a filtration, right? And the filtration has to have certain properties. And this means it has to be generated by some Brownian motion, the Brownian standard filtration. And I want that if I look at the quadratic variation of this local martingale B, that it's equal to T for all T in 0 to T. Okay, right? So the Brownian motion is just a special local martingale, namely the martingale, which has the quadratic variation equal to T. And this is an equivalent characterization of all these properties, like the, right? If you have a local martingale which has a quadratic variation equal to T, this has to have independent increments and it has to be normally distributed. Okay, proof. It's actually quick because we have done so many preliminary works, so we just need to apply now our martingale representation theorem and the time change characterization we have said before. Okay, but for completeness reason, right, the one direction is trivial, right? If I have a Brownian motion, I know it's a martingale, so in particular it's a local martingale, and I know that it's as quadratic variation equal to T, so this is the interesting direction. So first thing we note is, since our quadratic variation here is equal to T, so it's in particular finite, this implies the integrability of B, so this is actually a continuous martingale. And then can use the martingale representation theorem. So there exists phi in H2 such that the Brownian motion is given as a stochastic integral, and this is a Brownian motion with respect to a standard Brownian standard filtration. There exists a Brownian motion, so that we have this representation. For some Brownian motion B tilde. And what we also know is that if we calculate the conditional expectation, not the quadratic variation of Bt, this is nothing else than, right, using this representation of the integral from 0 to T of phi square ds, right, because the Brownian motion has derivation. And now we can apply our time change result. Change representation. It's the last theorem, so this theorem 6.2, with where we know the tau tilde, since the quadratic variation of the Brownian motion is just T, so the inverse is also just T. So this means Bt equal, so the time change Brownian B tau T is equal to Bt is the Brownian motion. All right, that's it. So this was not so hard because here we actually used our previous two main results. The first one is the martingale representation theorem, and the second one is our time change representation. And we will use this Levy characterization in the next video to prove how we can how Brownian motion itself behaves under change of measures. All right, thank you for watching the video.